In this video, we're going to introduce some of the fundamental concepts associated with sets. So a set is a collection of objects whose contents are clearly defined. In other words, we can definitively determine what is and is not contained within the set. Sets are often labeled using capital letters. So when I think of a set, I think of maybe something like just, I don't know, a box full of stuff. Think about it like a box full of stuff. How so? Well, we know definitively what's in the box. We have to know what's in the box. Also, if you were to just take the box and shake it around and things were to be rearranged inside the box, it's still the same collection of objects. So how does that relate to sets? Well, whenever we determine what's in a set, the order in which those items are contained doesn't actually matter. So as we talk about how we'll actually write or describe a set, keep in mind that the order we put things in our set doesn't actually matter. That's something specific to a set versus something like an ordered pair, where the order we list items in actually does matter. So with a set, order does not matter in terms of listing the contents. So each individual object in a set is called an element. So in order to indicate that something is an element of a set, we're going to use this symbol. So this looks a little bit like a lowercase e. This is actually the Greek letter epsilon. So this is a lowercase epsilon. So if we wanted to say that element A is contained in the set A, so this would be the label for the set, this would be whatever the element in question is, we would say A is an element of the set A. So the little epsilon symbol will go between them and it says that element A is an element of set A. Now if we want to say that something is not in a set, we will take that epsilon and we'll place a slash through it. So we use this kind of notation a lot in mathematics. For instance, if we want to say something is equal versus not equal, we can take an equal sign and we can place a slash through it. So putting a slash through anything essentially takes the same operation but adds in the word not. In other words, it negates that operation. So if we wanted to say that element B is not an element of set A, this would be the notation we would use to describe that. Now, sets individually can be described using their sizes. So a set without any elements, it's possible we can create a set that doesn't actually contain anything, is called the empty set. And the symbol representing the empty set is going to be an O with a slash through it. This set is often used if we're solving an equation and we want to indicate that there's no solution. We could either say that there's no solution, or we could say that the solution set is the empty set, which just means we can't actually find any solutions, and so the set of solutions would be empty. Now, if we do have elements on our set, but they can be counted, in other words, there is an end to the set's contents, then we would say that the set is a finite set. A lot of sets are not like that though. So for instance, say we took the set that contains all the integers. Well, that's going to be all our positive counting numbers and 0, and then all of the additive inverses of our counting numbers. In other words, imagine taking those numbers and putting a negative in front of them. Well, that set is infinitely continuing in either direction. So that set, we couldn't actually count out or make a list of or enumerate all the elements in that set. So any set like that is said to be an infinite set. So we can describe a set using references to size. We can also describe contents, and this is going to be the most important thing in terms of how we use a set. We can describe the contents of the set in two ways. So number one, what we're going to call the rule method. You'll sometimes see this called set builder notation. And number two, the list method. In other words, we're just going to make a list of the items in the set. The list method is sometimes called roster method because we're just making a roster of the items in the set. So for example, set notation would be something like this. So the curly braces, let's start with that. If we're going to denote a set, in other words, contain together all the items that are in our set, the opening and closing notation is going to be a pair of curly braces. So these curly braces indicate that all the contents make up what we're calling a set rather than another type of collection of objects. So once we open the curly braces, we're going to define a variable. It can be any variable we want. This variable is just a generic variable. So in this case, we've chosen X. So we draw the X, and then we're going to draw a vertical line after that. The way we read those two items is all X such that. That's the way that is read. And then after the vertical line, we have some type of description of what x looks like. In other words, all the different values x could take on. If x is a variable, x could take on different values. Well, whatever comes after that vertical line is going to involve some type of description of x. So it could be a word description, it could be a description involving maybe inequality symbols, it could be a lot of different things. So essentially what's happened here is we've defined a variable, and then we've defined, using a description, all the different values that this variable could take on. So the way we would read this is the set containing all x such that x is an uppercase vowel. So that would be the set builder notation representation for this particular set that we're calling set S. Now we could also translate our rule notation or our set builder notation into list notation. What that would require is interpreting what this notation means and then just making a list of all the individual elements within this set. So if this set contains all x such that x is an uppercase vowel, we know how to make a list of all the items in this set. So our elements would constitute a capital A, a capital E, a capital I, a capital O, and a capital U. So those would be the individual elements listed out in this set. So either notation is considered appropriate. It just depends on the situation we're in. Now, if we want to delve more closely into specific contents in a specific set, usually the list method is going to be more helpful. So in a lot of situations, we may have a set described in the rule method or using set builder notation, and we may have to start our problem by translating into list method just so we can see the contents of the set more specifically. So let's do some practice with notation. So we want to write each set described using the list method, and then we want to determine whether the set is finite or if the set is infinite. So our first set in the rule method is all x such that x is a day of the week. So in other words, anything contained in this set is a day of the week. So if we wanted to make a list, wanted to list out the contents of this set, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. Now one thing I do want to emphasize, particularly from this example, is there's a specific order that these were written in. Maybe some people would have logically started with Sunday, maybe some people start with Monday. The point is, the order doesn't matter. It doesn't matter which order we list them in. If we change the order of the days in this case, it's still the same set. It's still a set of all of the days of the week. However, in most cases, when we start to make a list of the items in a set, we typically like to list in some type of meaningful order. So in this case, we're talking about days of the week. More than likely, we'd want to start with whatever day the week starts on and then progress in order to whatever day the week ends on. So technically speaking, the order we make that list in does not matter, but having a meaningful order to the items in our set, if at all possible, is usually a good thing to do. So making a list in a particular order is usually going to be something we want to do. So this is a set containing something that isn't numeric. Now what about a set that does contain numeric items? Because that's going to be what we're focused on. So all x such that x squared is equal to 16. In other words, we want to determine what values could this generic variable take on such that this relationship is satisfied and we know that we could square x and get a 16. Well, there's actually two different values that would make this true. 4 is the one that immediately stands out, but keep in mind, if we squared -4, that would also give us a 16. So in this case, both -4 and 4 would be contained in this set, and they're going to be the only elements in this set. Now again, notice they're written in a particular order. When we're talking about making a list of numbers, 9 times out of 10, we're going to list smallest to largest. In other words, most negative to most positive. So in this case, we'll make a list of -4 before 4. Technically speaking, the order does not matter, but it's considered standard practice to write in this order. And then last but not least, all x such that x is an odd positive counting number. So by saying counting number, we're talking about numbers that are not fractional. They're rational numbers, they're whole numbers in this case. And we want the numbers to also be odd and positive. okay? So the first odd and positive counting number would be 1. And then if we're counting odd numbers, then we skip the number right after 1, which would be 2. So the next odd positive counting number would be 3. We'd skip the next one, which is 4, because 2 and 4 are both what we consider even numbers, so they would not be contained in the set as described. So first 3 elements in this set would be 1 and 3 and 5. Notice this set, if we were going to start with the lowest element, would start at 1 because we're looking at positive numbers. So none of the negative numbers that would be less than 1 are contained in this set. Now, notice I didn't actually make the whole list. Why didn't I make the whole list of numbers in this set? Well, can we actually make the entire list of elements in this set? Think about that. If we're talking about counting numbers, the idea with counting numbers is we can continue counting indefinitely, and sets like that never actually end. So in order to indicate what is actually contained in this set but not have to make a huge list of items, we establish a pattern using no less than 3 elements. We have to have at least 3 elements. This establishes our pattern based on how that set is described in rule notation. And then we use an ellipsis, which is 3 dots, in order to indicate that the pattern continues in the same way indefinitely, so on and so forth. We can use this ellipsis in multiple ways. So this out of the 3 is the only infinite set. The other 2 sets are going to be finite sets. We can make a list of how many items are in the sets. We can count how many items are in the sets. This particular set is an infinite set. There's no way we could actually make the list of everything in this set. So this is one way that the ellipsis is used. It's used to indicate that our set is infinite and that we can't actually make a list of everything in this set. An ellipsis can also be used with a finite set, but maybe a set that's large. So for instance, say we wanted to make a list of all of the counting numbers from 1 to 100. Well, that's going to be a large set for sure, but technically speaking, we could list out everything in that set if we wanted to and we were sufficiently motivated. However, we can use this particular ellipsis notation to handle a situation like that as well. So again, say we wanted to make a list of all the counting numbers from 1 to 100. We could list out 1, 2, and 3, which establishes our pattern. It tells whoever's looking at the set, this is the pattern involved and I've established this pattern. And then we can place an ellipsis, which just means continuing in the same fashion. And then after the ellipsis, unlike this set where it just continues on indefinitely and it never ends, if we want to use an ellipsis in a finite set, after the ellipsis we could just put maybe the 99 and then the 100, indicating that we have a particular pattern, but that pattern concludes, and it concludes with some specific numbers. So this is a situation where the order we write the elements in very much matters. Again, in general in set notation, the order we write items in doesn't matter. But if we're planning to use an ellipsis in order to establish a pattern among whatever's in the set, then we definitely need to have some type of order, because 9 times out of 10, the order is related to whatever the pattern is that we're trying to establish. So that's a little bit with notation. So again, when listing the elements in a set, just to summarize, order does not matter. So this means that 2 sets with the same contents are going to be equal, regardless of how the contents are listed. If we take one particular set and rearrange the elements, it's exactly the same as any other representation that has the exact same elements in it. However, again, it is typically best to list our contents in an order that is meaningful. In other words, maybe smallest to largest with numbers, alphabetical if we're talking about words, or like those days of the week, there was another order that was meaningful, and so we used that particular ordering. Okay, so that's just a little bit of context for what we're going to talk about for the rest of this section. We're going to use these set concepts to prepare for our discussion of probability. So that's going to be the sort of end goal for our discussion of sets, and then a couple things we're going to discuss in the next couple of videos. So let's talk about what a subset is. So a set A is a subset of the set B if all elements in A are also in B. So the way we indicate this is that A is a subset of, that's how we read this notation. Looks kind of like a C. I think of it as like a contained in. A is contained in B. So what does it mean to say that A is a subset? Well, it means A is also a set, so A and B are both sets. But what we're saying is that if we made a list of everything in A, then all of those items can be found in the set B. So if you were to think in terms of size, A is typically going to be a smaller set and B is going to be a larger set. So by saying that A is a subset of B, we're saying, in a sense, we could find everything in the set A contained in the set B. It's almost like the set A itself is contained in the set B. That's technically not what's going on, but from a conceptual standpoint, you can kind of think of it that way. So everything in A is contained in B, and then B potentially has some other elements as well. And this is going to be the notation for that. Now, just a heads up, in a lot of situations, a lot of textbooks are going to use this notation, but they draw a line underneath it. Technically, there's a slight distinction between those two notations, but they're used relatively interchangeably. So you may see this subset notation, but maybe the little c and it may have a line underneath it as well. So just be aware, if you see that, it means the same thing. It means we're talking about subsets. Now, if we want to say that A is not a subset of B, just like with that epsilon notation, we would just place a slash through whatever our operator is. So A is a subset of B, A is not a subset of B. Those would be our two notations. So let's do a couple of examples. It's going to be easiest to do this just using true, false. So if we have a particular statement using these operators, can we determine whether or not it's true or false based on the sets we have defined? So set A is going to be the set containing the elements 0, 2, 4, and 6. So that set was represented in list method as are B and C. B contains the elements 0, 1, 2, 3, 4, 5, 6. So all the counting numbers from 0 to 6. And then C contains the elements 2, 6, 0, 4. We want to determine whether or not each of the following are true or false. Okay, so first statement, A is a subset of B. What this means is it's asking, are all the elements that are contained in A also elements that are contained in B? Well, we have to go to the list of elements to make that determination. So the elements contained in A are 0, 2, 4, and 6. In order for A to be a subset of B, we have to be able to find every element in A also somewhere in B. So it's a matching type activity. So 0 matches to 0, so that element in A is contained in B. 2 matches to 2, 4 matches to 4, and 6 matches to 6. So every element in A is also an element in B. And notice that B has some other elements as well. What we're interested though is just, can we match everything in A to a matching element in B? In this case, we can. So A is a subset of B is a true statement. Now, what about the other way around? B is a subset of A. Well, same idea. We're taking the elements in B and we need to see if we can match every element in B to an element in A. So 0 is in B, we can match that to an element in A. 1 is in B. Well, if we go through the contents of set A, notice we don't have a 1. So we can't match that 1 with something that's in set A. So as soon as we find an element that doesn't actually match, that's not contained in that second set, the one we're looking at in terms of one set contained in the other set, automatically we know that B is not a subset. So B is a subset of A. That's going to be a false statement. So what this means is that this particular operation is not commutative. If we flip the order of the sets in question, we have a completely different statement, and potentially we have a statement that becomes false. That's not necessarily going to be the case, but in a lot of situations, we will convert from something that's true to something that's false if we rearrange the order. Now, what about A is a subset of C? So again, we're looking at the contents of A. We want to make sure we can match them to the contents of C, and C potentially has some other elements. So we have a 0, we can match that with the 0 in set C. We have a 2, well, that matches as well. We have a 4, we can match that. And then we have a 6, we can match that as well. So that means every element in A is contained in the set C. So every element in A is also an element in the set C. That means that A is a subset of C. Now, A subset of B, A subset of C, notice there's a pretty distinct difference in those two situations. When we were comparing A and B, all the contents in A were contained in B, but B also had some extra elements that weren't included in the set A. Whereas if we're looking at A and C, notice all we've done is match what's in A, and C doesn't actually contain any additional contents. So this is a little bit different of a comparison. However, if we just go back to the definition for a subset, all elements in the first set are also contained in the second set, then that criteria is satisfied in this case. So even though it's a slightly different comparison between A and B and A and C, A is a subset of C. So notice A and C have the same contents. All that happened in set C is the contents were rearranged for some reason. So A is a subset of C is a true statement. Now, further than that, A is equal to C. Can we say that? Well, equal just means all the contents are the same. Every element is the same, but remember, order does not matter. So equality can be established regardless of the order we write the elements in. As long as all the elements are the same, we can say that the sets are equal. So because A and C have all the same contents, A doesn't have anything extra that C doesn't have, C doesn't have anything extra that A doesn't have, we can say that A and C are the same. Another way of saying this is that A is a subset of C, and C is also a subset of A. If both statements happen to be true, then that's our indication that the two sets are actually equal. Now, what about B is a subset of C? In other words, we're looking at all the elements in B and matching them to C. Well, I start with 0, so 0 can be matched to an element in C. Then 1. 1 cannot be matched to an element of C. So we know that B is a subset of C has to be a false statement. Now, we haven't used the not notation, so C is not a subset of B. C is not a subset of B. In other words, we can't match all the elements in C to an element in B. So we have to go about the same process, but now we're trying to determine, is it impossible to match everything in C to something in B? Well, same idea. So we have our 2, 2 matches, 6 matches, 0 matches, and 4 matches as well. So if the statement we're looking at is C is not a subset of B, well, we just showed that everything in C can also be found in B. So that means C is a subset of B. So the statement C is not a subset of B would have to be a false statement. Now, this last one is kind of a strange one to propose, but it's something we do have to consider. What does this mean? Well, remember, this notation means the empty set. It means the set containing no elements. The set containing no elements is a subset of A. That's the statement in question. So again, you have to go back to the definition of a subset on this one. All we're asking is, is every element in the empty set also an element in set A? Well, the empty set doesn't actually contain anything. So even though there aren't any elements in the empty set, we can match every element in the empty set to an element in A. If there aren't any elements in this set, then matching is not really something we're physically doing. But the empty set is contained in A because, technically speaking, all of the elements in the empty set, there are none, we know that, are also contained in the set A. This is almost true by definition. We just think of this as being a true statement. This is actually going to be a true statement in any situation. The empty set is a subset of another set is true in any situation. That's always going to be a subset of our set in question. Okay, I want to talk about some set operations now. So we know what a set is. We've talked about a subset, what that looks like, some of the notation for that. We also have different ways that we can combine sets together. We can compare sets. And then I also want to look at Venn diagrams, which are going to allow us to take sets that we're looking at maybe just in a list form and represent them a little bit more visually. But the idea is that now we're comparing two sets together. So maybe one set in the context of another, or two sets related to one another. What do they have as commonalities? What do they have as differences? So Venn diagrams, most people have seen Venn diagrams at some point in their academic career. I remember, I think, seeing them for the first time, maybe late elementary school, early middle school, something like that. When you see a Venn diagram for the first time, you see it in a very specific form. But fundamentally, the form you're used to seeing it in is not necessarily what a Venn diagram is in the most basic sense. So a Venn diagram is just a picture, so it's going to picture a set contained within the context of another set, what we're going to call the universal set. So think of it as taking a whole big collection of elements and then condensing them down a little bit further into an additional set that somehow groups elements in a meaningful way. So this is not what you're used to seeing for a Venn diagram, but this is a Venn diagram. We're going to draw a rectangle for the universal set, which we're going to call U. So that capital U is always going to be used to label the universal set. Think of this as a big group of all the elements that we're considering. We're considering a specific group of elements to then potentially be grouped further or potentially not be grouped further. So within the context of this universal set of elements, we have another set. We draw this as a circle, and we're calling this set A. So think of set A as elements in the universal set that for some reason have been grouped a little bit further. So maybe they just have a little bit in common. So say, for instance, the universal set is the set of all students in a particular class. And maybe I'm interested in students that have a particular major. Maybe that's sort of the situation I'm in, and I want to focus on those particular students. I might represent this set or define this set in terms of those students who have a particular major. So maybe they're planning to major in business, something like that. The universal set would be everyone in class, and then everyone who is in the class but also a business major would then be grouped a little bit further into this set that we're calling A. So there would still be some names outside of the circle. Those would be students who are not majoring in business. Notice that the circle is also contained inside the rectangle. So all of the business majors that have been further grouped, well, they're contained in A, they're contained in that special set, but they're also still contained in the universal set because they're still students in the class. So any further groupings we do are going to also still be within the context of our universal set. They've just been grouped a little bit further because for some reason they have something in common. So every element in A, another way to say that, is also an element in U. It's simply been further grouped based on whatever sort of situation we're interested in. Now, when a Venn diagram contains more than one set, which is what we're used to seeing, we can also define the following, which we consider to be operations performed on our sets, somehow combining them together or comparing them. So the first operation is what we're going to call a union. So we're taking two sets, in this case A and B, and we put a big U between them. Now when you use something like this in your homework, something like that, if you're trying to type this symbol is not the U on your keyboard. The U on your keyboard is a letter. The U on your keyboard is the universal set. This is actually a mathematical operator. So in most cases, if you want to indicate that you're using a union, you're going to have to use a symbol that's created in a different way. Usually it'll be contained on whatever specialized keypad you have to type in mathematical symbology. So the union of A and B, if we were to represent this using the rule method, in other words, describing what's in this set, it's going to be all X such that X is an element of A or X is an element of B. Now I want to look at this word or, because the way we interpret or mathematically and the way we interpret or just in common speech are potentially a little bit different. So there's two definitions of the word or. One definition of or is an exclusive or, and one definition is an inclusive or. So exclusive or is typically the way we use the word or in common speech. So that would be something like, I can take an English class at this time or a math class at this time, But based on how the word or functions in that situation, we know we couldn't take both. So or would mean one or the other, but not both. So that would be exclusive or. That's what it means. One is true or the other is true, but both can't be true at the same time. Now, on the other hand, inclusive or means one or the other and possibly both. So I can go to the mall with this friend, or I can go to the mall with this friend, or maybe we can go together. I can go with both of them. That's going to be the version of or that we're interested in mathematically. So mathematically speaking, when we see the word or, we're talking about the inclusive or. So the first statement could be true, or the second statement could be true, but if both are true, then that case is still included. We're still considering situations where both are true at the same time. So it's not just one or the other, strictly one, it could be both at the same time. So that's how we're going to interpret the word or. So if we have our standard Venn diagram, this is what you're used to seeing. You may not be used to seeing the rectangle, you're probably just used to seeing the overlapping circles. But now we still have our universal set, the context for our problem. In other words, again, think of it like the list of all the students in a class. Now we have two sets where we've further grouped the elements, but we've overlapped these sets. So A is the first circle, B is the second circle, and we've overlapped the sets to indicate that it's possible that A and B have some elements in common. It's possible that maybe if we're talking about majors, maybe we're looking at business majors and science majors. Maybe someone's majoring in business and in a science field at the same time. Those people would be located in the overlap. Now, when we're talking about the union of set A and set B, we're talking about all the elements in A, which would be anyone that's anywhere in set A, including that overlap. People in the overlap are in set A. Also, anyone that's anywhere in set B, that would be everyone in the circle for B, again, including that overlap. If we were to take these two sets and take the set of elements that's contained anywhere in the pair, either it's just in one of them, it's just in the other, or it can be both together at the same time, that bigger combined set represents the union between the two smaller sets. So this looks kind of like set addition. It's kind of like taking the two sets and adding them together in a sense. We're taking one bigger set that results from combining the two smaller sets together. So that's going to be the union of these two sets. Now, another operation that could be used to combine two sets is called the intersection. So this is going to be an upside down U. So standard U is union, upside down U is intersection. When I look at this, I think this looks kind of like a little lowercase n. So think N for intersection. That's how I remember which one is which. If we were to describe what's in the intersection, it's all X such that X is contained in A and X is contained in B. That word and means both at the same time. It means it has to be an element of A and it has to be an element of B at the same time. If we were going to think of that in terms of the Venn diagram, that's going to be the section and the set of elements that are contained in both A and in both B. That's the set overlap. That's where the two sets intersect. It's where they cross over. So any elements considered to be in the crossover, the business majors and the science majors, the ones who are majoring in both, that's going to be elements contained in the intersection of our two sets. We have a third operation that technically only requires the use of one set, but can be applied to more than one depending on the situation we're in. It's called the complement. So A complement is going to be A with a prime. So that looks like an apostrophe. Mathematically speaking, we call that a prime symbol. If we were to describe what's in this set, it's going to be all X such that X is contained in the universal set. In other words, it's somewhere in our rectangle of elements under consideration. And it's not contained in A. So it's an element somewhere in the universal set, and, or maybe a better word would be but X is not contained in A. So think of the elements contained in the rectangle for U. Some of them are outside of A and B, some may be in A, some may be in B. If we're taking the complement of A, we're essentially covering up A and saying take everything else that's anywhere else in the universal set, but just pull out anything that would be contained in the set A. So it looks kind of like set subtraction. Think of it like taking the whole Venn diagram and just pulling out the circle for A. Now notice that that is immediately going to eliminate that intersection. The intersection represents elements that are in A and B at the same time. Well, if we're excluding A, if we're saying the elements in question can't be contained in A, that includes elements that are only in A and elements that would be considered to be in the intersection, in the overlap between A and B. So if you just imagine covering up A and then looking at the rest of the diagram, covering up A and then looking at the rest of the diagram represents the complement for the set A. Now at the same time, if we were going to do the complement for the set B, that would be cover up the set B, subtract it from the diagram, from the situation, and then just look at the elements that are left at other locations there in the universal set, and then potentially grouped a little bit further into our other remaining set. So we can define these operations based on a Venn diagram, which again is just a visual representation of our sets and how they relate to one another. We can do the same operations when our sets are in list form as well, though. It's kind of like the subset operation. So we're just looking for maybe things that our sets have in common. Maybe we're uniting two sets together. One thing that is going to be important if we want to execute these operations, though, is we can't just have a set A, a set B, a set C, however many sets we want. We also have to have the universal set defined. So this is the whole list of elements. This is all the elements under consideration that have then been further grouped into smaller sets. So if we were to talk about subsets, A, B, and C are subsets of this larger universal set. So the universal set contains all of the elements under consideration that have been further grouped into smaller sets. So based on these definitions and based on what we now know about these set operations, what they mean, we want to find each of the following. So first, we want to find A union B. So that's going to be all the sets that are in A or in B. So anything that's contained in A makes it into the union. Anything that's contained in B makes it into the union, including any elements that they share if they happen to share any elements. So think of it like taking A and B and just combining them together. It's like you're adding the two sets together. Now the one distinction, the one spot where we have to be careful, notice if we look at A and B, A has 3 and 6 and 9. B doesn't have a 9, but that 3 and that 6 are shared. When we combine these two sets together and take their union, we're only going to list those shared elements one time. So although there's a 3 and a 6 in A, and there's also a 3 and a 6 in B, we're only going to make a list of them one time. So we have all the elements 3, 6, and 9, and then B also adds on our 4, our 5, and our 7. So if we were to make a list in ascending order, again, order technically doesn't matter, but it's a good habit to get into to have a meaningful order, then A union B is going to be 3, 4, 5, 6, 7, and 9. All the elements in A, all the elements in B combined together into one set. Now what about A union C? Now again, we're taking A, but we're uniting it with C. So this is going to be any element that's in A or in C and possibly both. So A contributes 3, 6, and 9, and then C contributes 4, 5, and 7. So if we were taking the union of those two, it's going to be 3, 4, 5, 6, 7, 9. Now notice A union B and A union C are actually the same thing, but B and C were not the same. The reason the unions ended up the same, even though those constituent sets weren't the same, is because the additional elements in B, remember, those were duplicates. Set notation is such that in general we don't write duplicates. So if something is duplicated in real life, if we're representing that situation using a set, we only write the duplicates one time. So that's why those two unions ended up being the same, even though the constituent sets weren't actually the same. Now, what about an intersection? So A intersect B. What this says is elements that are in A and in B at the same time. In other words, we're looking for commonalities. We're looking for what A and B have in common. So it's a matching thing, kind of like the subset situation. So A contains a 3, well, B also contains a 3. So that means the intersection contains a 3. A contains a 6, B also contains a 6, so 6 is also in the intersection. And then A contains a 9. But notice that B does not contain a 9, so that 9 is not going to be in the intersection. Now, I just went through the set A. Do I have to go through and do the same thing for the set B? The answer is no. If we didn't already find an element in A, we're not going to suddenly find something in B that matches something in A that we didn't already see. So we go through one of the sets, maybe just go through the smaller set, that's going to be easier. We're just looking for elements that match. Any elements that match are contained in the intersection between those two sets. So in this case, A intersect B is going to be the set with the elements 3 and 6. Now what about A intersect C? A has 3, 6, and 9, but C has 4, 5, and 7. So if we're looking for overlap, if we're looking for commonalities, A and C don't actually overlap. They don't actually have any commonalities. So if we were to define their intersection as a set, their intersection is actually the empty set. If they don't have anything in common, but we want the set of things they have in common, then the set of things they have in common is a set that doesn't have anything in it because they don't have anything in common. So their intersection is going to be what we call the empty set. These two sets have a specific relationship. We would say that A and C are disjoint. Disjoint is the official term we use if we're talking about two sets that don't have anything in common. We would say they are disjoint. If we join them together, they would be completely adding new elements from either side, and also they're completely separate. That's more what we want to think of it. If in terms of a Venn diagram, if we were looking at A and C represented by a Venn diagram, we wouldn't actually need to draw two circles that overlap because A and C don't have any overlap. So we could have two circles, but the overlap is empty. In other words, there's no way to join the two sets together in terms of considering overlap. Now, what about complement? So A complement. This one is a little bit more challenging. It's probably the most challenging operation just conceptually. A complement means take the universal set, which we haven't had to use yet. Remember, the universal set is all of the elements under consideration that have been further grouped into smaller subsets. So take the universal set, and if we're taking A complement, we're taking the universal set and we're subtracting out all of the elements that were matched to the set A. So we're subtracting out A from the universal set. Well, A contained the elements 3, 6, and 9. Because this is the universal set, all the elements in A are also elements that are in that universal set. But if we're taking the complement of A, we're taking those elements that were in A and we're pulling them out of the universal set. So the universal set minus A, if you want to think of it that way, we're going to take out the 3, we're going to take out the 6, and we're going to take out the 9. So that's going to leave us with 1 and 2, 4 and 5, and then 7 and 8. That's going to be A complement. So everything that's in the universal set except elements that were contained in the set A. Now what about the set B complement? Same idea. We're taking the universal set. We're looking at elements in B. Every element in B is also an element in the universal set by definition. But if we're taking B complement, then we're taking the universal set and we're removing all of the elements that are in B. So we're removing 3 and 4 and 5 and then 6 and 7 as well. Well, what does that leave us with? If you cover up what we've already taken out, we took out all of the numbers from 3 to 7. We still have a 1 and a 2, and then we still have 8 and 9. So that's going to be B complement in this case. Well, now let's put it together. What we're going to use sets for, we're going to continue to build on these ideas of a set, a subset, all these different operations. Typically, we're going to use in terms of counting. The goal is going to be able to count what happens in some different situations. Not counting 1, 2, 3, 4, 5, not counting like that, but specifically counting the number of ways we can accomplish a particular task or a particular operation, or maybe a sequence of tasks and operations. So counting how much is in a set is going to be the skill we work on from here on out. So we have a particular notation if we're going to talk about how many things are in the set, not the actual contents, just how many unique items, distinct items are in the set. So the number of elements in a set A is denoted as n of A. That's the way we would read this. So lowercase n indicates that we're talking about the number. Sometimes you'll see this called the cardinality, or the cardinal number. That's how many elements are in the set A. So this can be determined from a rule or a list. If we can describe what's in the set or make a list of what's in the set, then we can count how much is in the set. Or we can also do this from a Venn diagram. So the Venn diagram is going to be especially helpful if we're talking about counting things that are in more than one set at the same time, which is what we're going to look at here. So essentially, we're going to take this idea of counting, we're going to combine it together with our set operations, and then with what we know about how we can draw a Venn diagram. Okay, so an election poll of 100 voters produced the results in the table below. So we've categorized people, whether they were male or female voting, and then who they voted for. Did they vote for candidate A? Did they vote for candidate B? Okay, let the universal set U be that set of 100 voters. So in other words, we're taking all those voters and then we're grouping them further into sets. We're going to let A be the set of voters for candidate A. We're going to let B be the set of voters for candidate B. We're going to let M be the set of male voters and W be the set of female voters. Okay. We want to find each of the following sets based on these sets as labeled and as described. So we want to find not specifically the set, but the number of elements contained in the set. So the first one we want is going to be N of A intersect M. Well, let's think about what that means. We have to think about what that set is. In order to count how many elements are in the set, we need to think about what that set represents. So everything that's in the set A that's also in the set M is what that symbol means. It means it's an element of A and it's an element of M at the same time. Well, what do we know about elements in A? We know the elements of A are people who voted for candidate A. We know the elements of M are people who were male voters. So A intersect M is people that voted for candidate A and are also male. We can determine that from this table. This table has organized information in such a way that we can immediately determine what this value is and what this set represents. So they voted for candidate A and they're also male. So look at the intersection for that, candidate A and male. So based on the information we have, we know there would be 23 people in that set, people who voted for candidate A and are male at the same time. Now, what about A intersect M complement? This is a little bit more complicated. Let's think about what M complement means. M complement means everyone that's not contained in the set M. Well, if you think about what M represents the set of male voters. M complement is everyone who was not categorized into the set of male voters. Well, if you think about what that means, either you are put into the category of male voters or you're not. Well, if you're not, what category were you put into? You had to have been put into the category of female voters. So M not means not male. It means in this case female. So we're saying everyone that voted for candidate A and was not a male voter, in other words, was a female voter. So we're looking for people who voted for A, who in this case are female voters, they're women voters. So they voted for candidate A, and they happen to be women, not men, so they fall under the different category. So that one is going to be 29. We have 29 elements in that set as described. Now, what about M intersected with not A? These two are not the same thing. Notice now we're taking the complement of A, whereas before we were taking the complement of M. So we're saying this person falls under set M, but does not fall under set A. In other words, they fall into the category of men, but they do not fall into the category of people who voted for candidate A. Well, if they didn't vote for candidate A, automatically we know they voted for candidate B. They have to in this case. So we're looking for people that are both M, that are both male, and voted for candidate B. So they voted for candidate B and they're male. So there's going to be 26 people in that set. And then last but not least, what happens if we take two complements at the same time? Well, again, think of just introducing the word not in place. Not is a word we could use to describe the complement. So A complement intersected with M complement. So not in the set A and not in the set M. Well, if you're not in the set A, if you didn't vote for candidate A, automatically you voted for candidate B. So we know that. If you're not in the set M, you're not male, that means in this case you had to be a woman, so a female voter. So didn't vote for A and is not male, another way of saying that is you voted for B and you're female. So you voted for candidate B and you're a woman. So there would be 22 people in that particular set. So based on these numbers, we want to draw a Venn diagram with circles labeled A and M in order to organize this information. Now we have 4 sets defined. We have the set U, which I guess makes a 5th set, and then we have the sets A and B for people who voted for different candidates, and we have the sets M and W for male voters versus female voters. So why would we draw a Venn diagram that only involves 2 of the 4 subsets of the universal set? Well, Venn diagrams help us organize and synthesize and sort of shrink down the information and the categorizations we have. How does this work? Well, let's think about the set A. If we're drawing a Venn diagram, one of our circles is going to be a circle representing the set A. So anyone who voted for candidate A has to fall into that set. Now, what can we say about people who fall into this set? Okay, they're in that set, so they voted for candidate A. If we're taking circle A and circle M and they overlap, people in the overlap voted for candidate A and are male. Well, what happens if they don't fall into the overlap, but they fall into the circle for A? So they don't coincide with the circle M, but they fall into the set A. Well, the only way, based on these numbers, based on the structure of this problem, the only way that can happen is they voted for candidate A, but they were not male. The only way that happens is if they voted for candidate A, but they're women. So by representing a set called M, automatically we can represent the set W by recognizing that anyone not contained in the set M, anyone anywhere else in the diagram that's not in the set M, automatically falls into the set W because M and W are opposite sets. In this case, they're disjoint. So we can represent W specifically just by recognizing that people categorized into M are male. Anyone not categorized into M automatically is going to be female. Now, same way with candidate B, we've only represented candidate A. What happens if someone doesn't fall into the circle for candidate A? Well, we know automatically they had to have voted for candidate B. So these are people who voted for candidate A but are not male. These are people who are both voting for candidate A and are male, so they overlap. What happens if someone just falls in the circle M? Well, it means they are male, but they didn't vote for candidate A. Well, if they're male and they didn't vote for candidate A, then that means they have to vote for candidate B automatically, just because we only have 2 options. So anyone in circle M that's not in circle A, we know is male and voted for candidate B. Well, there's one final category. Think about taking the complement of both sets. In other words, deleting everything, getting rid of A and getting rid of M. In other words, they didn't vote for candidate A and they're not male. Well, if that's the case, if they fall under those categorizations, they didn't vote for candidate A, we know they had to have voted for candidate B. They aren't male, we know they have to be female. So anyone outside those circles, but still in the rectangle, isn't male, so is female, and didn't fall in set A, so voted for candidate B. So notice the 4 distinct categorizations we placed people into can be represented using only 2 sets, just using this idea that you either fall into the set or you fall outside of the set. So 4 sets in total, 4 different categorizations in total, can actually be represented using only a 2-circle Venn diagram. And then based on the numbers we have, based on the descriptions for what each region of the diagram represents, we can then label. So notice the circles overlapping and then having the universal set on the outside defines 4 distinct regions in this particular diagram. So we have things that are only in A, things that are only in M, things that are in both A and M, and then also these surrounding regions. So that would be elements in the universal set that aren't further grouped into either of these sets. So this is just one example of how we might use a Venn diagram just as a way to organize information into a more visual style. So we'll use Venn diagrams in different situations. We'll use these set operations in different situations. And again, we're going to build on this with this idea of counting. The goal is to use sets or to count the number of items in a set, which we're then going to build into our discussion of probability.